Hey everybody. So this is hands down the number one most requested subject that people ask about as far as tutorials, which is TensorFlow. So with that being said, let's get into this TensorFlow tutorial. Diving in, let's start off with exactly what TensorFlow is. At its core, TensorFlow allows you to define and run computational graphs. Computational graphs are going to be inherent and you're going to hear it a lot and you're going to deal with it a lot when you're dealing with machine learning and AI. A lot of it boils down to essentially graphs, arrays, and graphical arrays. And so a computational graph is a way to represent mathematical operations as a graph of nodes and edges, which we'll get a little bit more into. And each node in the graph represents an operation, such as addition, multiplication, or a more complex function. And the edges represent the flow, the direction of the nodes. And then I'll try to make this a little bit more visual. It's exactly what you think of and what you're thinking of likely in your head as far as edges and nodes. I think edges and nodes are really simple to understand. So it's just mathematical concepts are your nodes, right? So in this first example, we've got two constants of 3 plus 4, and we have to give it a mathematical operation, so 3 plus 4 in this instance, which we can express as a plus b equals c, and then we print our result, and then we get 7. 3 plus 4 equals 7. And then so very straightforward, right? And then now you've seen your very first node, like the as simple as we can get as far as nodes, right? So diving in a little bit deeper and just kind of reiterating this. So nodes in a TensorFlow computational graph specifically represent the mathematical operations and or the variables. So each node performs a specific computation and holds a specific value. So each node is doing something individually, and that's an individual node. And then you can array can be like a graphical array. A computational graph can be composed of multiple nodes, like hundreds of nodes, millions of nodes, billions of nodes. And examples of nodes include addition, multiplication, convolution for neural networks, activation functions for neural networks, variables, trainable parameters for neural networks, and constants, which are fixed values that don't change during the computation, and placeholders, which are special nodes that allow you to feed input data into the graph. Nodes take 0 or more inputs and produce 0 or more outputs. And the computation performed by a node is typically a mathematical operation applied to its inputs. Nodes are connected to each other through edges to form the computational graph. So the edges are the glue, the connection, and again, edges are the direction. Edges in TensorFlow represent the flow of data between nodes. An edge connects the output of one node to the input of another node. Edges define the dependencies and the order of execution between nodes. The data that flows along the edges are tensors, which are multi-dimensional arrays. If you're familiar with programming language and arrays and multi-dimensional arrays, it's exactly what we're talking about. It's just building more complicated. It's arrays of arrays is what you get into, right? So you start off with your basic like tensor function and like your like in our very first instance there, a plus b equals c, and then we define another function, right? So like we define the direction of that function. So a plus b equals c, and then our direction of going forward, we would then have what would that be like d plus e equals f, and then you can go like forward from there. And then explaining exactly what edges are and what this looks like overall. So we can see this code example here, right, where we have the input and then weights 1, hidden layer, weights 2, and output. This is a very simple, this is a one-layer neural network that we're looking at here. That's exactly what it is, right? And then so it's taking and it's starting with the input, which is our first node, and then we have our direction, which is taking the output of the input and then going over to our our next input, which in this instance is weights 1, and then telling us the direction to go. And then important to note in this instance, like these directions don't have to go this way. So you can have, like, for example, back propagation of the weights, which does this exact same thing in reverse, right? So it takes the it starts with the output, and then weights 2, hidden layer, weights 1 and 2 input. So you can flow it either direction, any direction, right? It's what direction it flows in. That's what the edge is. The edge is the arrow. Simplest way to put it, right? And then so within this, and we build upon these edges and nodes to essentially get into computational graphs. And then a computational graph is essentially looking at it here. We have our essentially starting off with our input values, and then we can produce our from our inputs, we produce and we go along our flow, right? Like we follow our nodes and our edges, and then by following along in that flow, we can then get into essentially our computational graph, and our computational graph input output here, which is this. And then so this is very complex, right? But so this is like what the output of this result is. And then so when you deal with like TensorFlow overall, and you are building, you're essentially building computational graphs, and then these computational graphs combine, and then that's where you get into neural networks, and you combine layers of these graphs into different layers, and then that's essentially what a neural network is overall in a nutshell. But the power of TensorFlow, why you use TensorFlow and Keras in this instance, is to simplify this process, right? And then so think of it like TensorFlow is our backend. It would be like our Python language, right? And then we want to display this information, and we want a way to like have a front end, and then so that's where Keras comes in. And then so Keras is essentially a user-friendly library that enables you to quickly build and experiment with different neural network architectures, and it provides a wide range of layers, loss functions, optimizers, and other utilities to facilitate the development of deep learning models for various tasks, such as image classification, natural processing, and more, and natural language processing, and more. And so we're looking at essentially here training and bringing in a building a neural network from scratch. And that's exactly what we do here. We take in and we have our training data set. And then if you don't know what the MNIST data set is, it's handwritten, like a symbol, like handwritten numbers, right? So like 1, 2, 3, 4, all handwritten out. And then so we're utilizing that as our test training set. And then we're building, you can see here, all of these are layers of our neural network. So we're defining the architecture, and then we're defining, we'll go into essentially what we're looking at here with regards towards these activation functions, our optimizer, our loss function, and our metrics. And then we'll define out and go into all of these. But essentially what we can see here is, so in the code where you see optimizer equals Atom, activation equals ReLU, metrics equal accuracy, by just putting in Atom as opposed to anything else, or just putting in ReLU as opposed to anything else, that's what TensorFlow is doing. TensorFlow is doing all of that back-end work and all of that back-end functionality for us, and then we just have to pick the optimizer in this instance, which would be Atom in most instances, or pick the activation function, which in this instance would be ReLU, like ReLU and softmax, because we're doing a lot of we're doing image optical character recognition. So ReLU and softmax would be the two standard activation functions that we would use there. You can see I run this code, and then with this code, so this is the interesting thing, right? And then so when I very first ran this code, like epoch 1 of 5 and then like generation 1, it was clocking in around like 84-85% accuracy. And then so training the model up every single time, it went up, like it went up and up and up and up. So by the end of the first epoch, I was at 0.94% accuracy. And then by the end, like this isn't going to be maximum impressive to tech pros. Like some tech pros will still say like, yeah, this is still problematic, right? But it's 0.9908% accuracy. So 2 to 0.99, pretty good, right? Like 9.99% accurate. So overall, just through 5 epochs, which took about like 4 minutes overall of training on this data set, we were able to increase the accuracy by about 15% or so. Like we're like, yeah, about 15% in general. And then, so not only can you load a model, train it, and then do your thing with whatever you want with the model, you can flat out load in pre-trained models with TensorFlow and Keras. And that's kind of a major benefit of that, right? So in this, of the architecture. So in this first instance here, we're loading in the full model, and then I'm training it here. And then in this instance here, all we're doing is just loading in the model and then having it come in and then make a prediction off of this, so this is going in a blind prediction, right? And then so I load the model and then I give it an image. And then in this image, it's an image of a robot eating cereal. And then so its guess of a sewing machine isn't a bad guess for a very first guess. Remember, this is untrained on the data set. It's never seen my image that I uploaded before, and this is a model that I did not train on any level. So it's coming in like this would be called zero shot, where it's coming in cold to this image that I uploaded over here. And you can see here in the environment, and then you can see in the code where I give it the file to path for the image. And then so it's like 79% accurate that it's confident it's a sewing machine, 10% confidence that it's espresso maker, which is a good guess, and then it would also, like, its third guess would be a toaster. And then so sewing machines a pretty good, like, these are 3 pretty good guesses, right? It's a robot eating cereal, so like it's I don't know, it's hard. And then so that's how that works as far as bringing in a pre-trained model, right? And then so this last code here is kind of just the simplest way to bring in a model here. And then so showcasing what TensorFlow and Keras does as a whole, and kind of like, again, why you want to use TensorFlow overall is this right here, right? So this is bringing in and compiling for compilation a whole entire neural network. And then we're telling it what optimizer to use. We're telling it like several things about the model. The optimizer itself, the learning rate, metrics, the size of the model, the batch size for our training, and then our to train the model overall. And then we're telling it to use the Atom optimizer for training. And then so all of this would be a lot of code, right? Like individually, like each one of these individual arguments that we're feeding is being very much simplified by TensorFlow. And then so within TensorFlow, rather than having to know the math behind these things, we just have to know a few concepts. And then the concepts in general that we want to know are what we're looking at here. So optimizer, model, learning rate, metrics, and then we're going to go through them right now, right? So first of all would be this optimizer. And the optimizer determines how the model's weights are updated during training. Some popular optimizers include the SGD optimizer, which is a stochastic gradient descent. And then so saving you a lot of time up front, you're going to hear like 90% of what you're doing, you're going to hear one of 2 optimizers. You'll hear the SGD optimizer, or you'll hear the Atom optimizer. And then so I have other ones that are listed here, and then you can see all of the other ones that are listed here are derivatives of the Atom optimizer. So there's a reason why the Atom optimizer is very prevalent. It's because it's very good across the board. Like it's like there's not an optimizer that's been found that is like better, like just for generalized across the board. And then so beyond the optimizer, you have learning rate. And the learning rate determines the step size at which the model's weights are updated during the optimization process. Optimization, think of it as the training process. So it controls the speed and the stability of the learning process, how fast the model learns. A smaller learning rate leads to slower but more stable learning, while a larger learning rate can lead to faster convergence but may also cause instability. The default learning rate varies depending on the optimizer, but a common choice is a small value such as 0.001 or 0.0001, and then you can adjust the learning rate by setting the learning rate parameter when creating the optimizer instance. And then so faster learning rate means that you can train the model faster. Slower learning rate means that it takes longer. And then faster learning rate also you could run into further complications overall. And then so you can play around with that overall. And these are all like levers that you can push and pull, right? So the next lever that you can push and pull would be the loss function. And the loss function defines the objective that the model aims to minimize during training. It measures the difference between the predicted outputs and the true labels. The choice of loss function depends on the type of problem that you're solving. And then so this is like very specifically like what you want to do. So if you want a regression task, then you usually go with mean square error. If you're looking for classification, then you usually use binary cross entropy. But if you and then you have a categorical cross entropy and etc. Right? Generally speaking, you're going to use one of a few loss functions, and the loss function is very specifically dictated based off of what you're doing. So there's not a lot of play with the loss function overall, but it's something that has to be set. And metrics. Metrics are used to evaluate the performance of the model during training and testing. They're essentially like RLHF, or when you're giving feedback to the model, or tuning the model, or training the model. This is what you're training it to. You're not just like throwing random numbers out there. Just like go get them, tiger. You're training it to metrics. So they provide additional insights into how well the model is learning and can be used to monitor their progress. And then so you can measure like accuracy, precision, and recall are the big three. So accuracy, precision, and recall. And then there's like ROC curve, and then mean absolute error would also be like kind of the big five. Like generally these 5 metrics, you'll see 5 different charts, generally speaking. And then so next thing here is these last two are both related to specifically like the data set itself. And then so the first one being batch size. And then so batch size determines the number of samples that are processed together in each iteration during training. It affects the memory usage and the speed of training. A larger batch size can lead to faster training, but requires more memory, while a smaller batch size may result in slower training, but can be more memory efficient. Common batch size powers are powers of 2, such as 32, 64, 128, or 256. And you can set the batch size using the batch size parameter when calling the fit function. And then so, just as a general rule, you set the batch size based off of your GPU. And so if you have more memory within your GPU, you generally speaking can set a higher batch size, right? And then as it says, it's for the faster batch size can speed up your training. And so if you have a slower GPU, it's going to take you longer to train because you have to lower the batch size, and then which is training the model on less data at one time overall. And then so batch size, think of it like so if we have a document with 100 rows, and then we break it up into 25 rows each, that's 4 batches, right? But then if we break it up into 10 rows each, then we have 10 batches. And then how we break that up dictates our learning rate, our training rate in this instance. And then the very last one to go over here is epochs. And then epochs, the number of epochs determines essentially how many times that the model iterates over the entire training data set during training. So 1 epoch means that the model has seen each training sample 1 time. Increasing the number of epochs allows the model to learn more from the data, but also increases the training time. And then so you can set the epochs by utilizing the fit function. And generally speaking, most people, and for most models, you're setting the number of epochs on a data set between 3 and 5 epochs. And then the batch size, it's adjustable, right? Let's say it's 64 or 128 on the batch size. And then you set like 3 to 5 epochs. It's generally speaking how you break it down. Generally speaking, in like 90% of instances, you're going to use an atom optimizer. You're going to go through all of your metrics, and then you can train it based off of, and look at your metrics based off of steps. And then that's essentially, and then you have your loss function, which is dictated based off of exactly the what you're doing. So then whether it's like, again, like regression, prediction, classification, etc. And overall, this is essentially now through this, you now have a good understanding of exactly what TensorFlow is if you didn't before. And then so just very clearly kind of giving you an overall recap, TensorFlow is very specifically with regards towards computational graphs and graph functions. So we start off and then we deal very specifically with nodes and edges. And the basis, the building blocks of TensorFlow are nodes and edges. Nodes being like those mathematical equations and those constants, edges being the flow and the direction of that data. These nodes and edges build together into layers, into computational layers, and then which we can then build into computational graphs. And then using our front end, which is Keras, which is built on top of TensorFlow, we can simplify this entire process. And then rather than doing all of this complex math behind the scenes, we can get a kind of like our simplified interface to build out neural networks, where we essentially just have to put in a few parameters, like a few arguments into it, and then we can load models to train ourselves, or we can load models that are pre-trained overall. And then we can see here very simple and simplified example of all of that, and then everything that we're looking at here as far as what we need to know about TensorFlow overall. So real short, simple, and sweet. Like this type of content, please like and subscribe. Thank you very much.